So, well, most of you already know which is a block diagram based on. We have some information source that is going to transmit some information. We have to shape the transmitting signal in order to put it in the optical driver, and then we will use an LED for transmitting. We'll have a photodiode for receiving with some optical filters, and we will do the reverse process in the receiver part. Okay. Also, we'll explain later which kind of modulation schemes we can use for transmitting information and which are the advantages and the cons for each of them. But basically, we have to use an intensity modulation because we are transmitting or we are modulating the signal through the current, okay? The current that is going to feed the LED. So that's why the signal to be transmitted has to be positive and real. Okay, it's also this was explained also by Nicola some hours before, and that's why we can say that we are using a baseband transmission, which simplifies a lot the transmitter and the receiver. Okay. At the receiver part, we are detecting the optical power that is impinging into the receiver, and we are transforming this optical power into a current. Okay, that's why it is called a direct detection. But now let's focus on the hardware that is going to be employed for doing a prototype of visible light communication system. So why an LED? Of course, well, by starting the definition, LED is a solid-state semiconductor device which has the capability of changing the electrical energy into light, okay, into light energy. So it has many advantages, but here I have included some of them. Basically, it is energy efficient. It has a luminous efficacy larger than other lighting sources such as fluorescent or incandescent. The lifetime is of course larger, which is also a very good advantage. But not only that, but also it is free from hazardous substances such as mercury that was used in the previous fluorescent that is being used right now also. But what is most important is that the LED has the capabilities for higher speed. Okay, it can be modulated at higher speed that allow us to transmit information. Okay. Also, it gives us the possibility of controlling the kind of control of color that we can use. Also, to perform in a dimming mode and so on and so forth. The prices are getting lower, more and more. And the LED is used everywhere, so we can create a VLC system basically everywhere, okay, outdoor, indoor, and in any kind of scenario, which is good. So in several years, almost 100% of the lighting sources will be based on LEDs. So now, how does an LED work? So I'm pretty sure that all of you, or most of you, already know what is the electroluminescence. This is the name the name of the process that is taking place within an LED. Okay, an LED is basically a diode which is composed by two types of semiconductors, P-type semiconductor and N-type semiconductor, containing holes and electrons, okay, respectively. And then if we apply a voltage between these two poles, we can create a current. Okay, so the positive and the negative charges are forced to move in opposite direction. And when they meet each other, of course, the electron has a lower energy a hole has a lower energy than an electron. And this way, in order to, when they are combined, some energy is released. Okay, and this energy that is released, it is made by means of a photon. Okay, so this photon is the light that we are seeing. And in order to make it practical, to make it feasible, it has to be installed within a package. Okay. I have included here some video which is really intuitive. Okay, it is made by Lyon, which is a company for lighting sources, and I recommend you to have a look at it. But now let's talk about which kind of LEDs exist in the market. Well, these are the two most typical LEDs. We have a phosphor-coated LED, which is made by a blue LED chip and also with a phosphor converter. And then, okay, this is the spectrum of this kind of LED. We have some energy in the blue wavelengths, let's say, okay, and also some energy in this yellow part, which is done by this phosphor-coated, okay. It has some pros, such as the low complexity, the price, and also it has a very good color rendering index, which is a measurement in order to get to know how far we are from the natural light. Okay, so always when we have to, well, don't forget that we have to illuminate and to transmit data at the same time. So from the illumination perspective, we have to create a light which is the most similar as possible as the natural light. Okay. But also we have the multi-chip LED, which basically we have several LEDs in one. Okay. Here I have included an red, green, and blue LED, but there are some others, including a fourth color, for example, amber. Okay. By the combination of these three colors, we are able to provide the white light. Okay, and we can see here as in the spectrum we have energy in the wavelengths belonging to these three colors. Okay. This kind of LED allow us to have some new modulation schemes, such as color shift keying, that by having some combination in the power for these three colors, we are able to transmit some information. But not only that, we have the possibility of doing some multiplexing techniques, such as wavelength division multiplexing, in which we are able to transmit 3 channels in parallel. Okay, and at the receiver side, by using some optical filters, we are able to distinguish which information has been transmitted through these 3 channels. And of course, we are multiplying by 3 the bandwidth. Okay, so we can achieve larger data rate in this kind of LEDs. But not only this type of LEDs, there are some others in the market, such as organic LED, but the performance is not as good as the previous one. So the bandwidths that are possible to be achieved here are lower than with the other 2. Also, the lifetime is a bit lower. So the other 2 are more typical to be used. Okay, and also we have micro LEDs with which we can achieve larger bandwidths. Okay, so in the order of 400 megahertz, which is huge for communication. And this is possible because they are micro LEDs and they have a low capacitance. So the lower the capacitance is, the larger the bandwidth can be. Okay. So these 2 both are typically used for flat panel displays. So basically they are used for advertisement, also for monitors and so on. And it's good to know that we can transmit information also with this kind of LEDs. But there is not a unique LED which is the best solution for any application. Okay, so of course, depending on the application, depending on the scenario, it's better to use one LED type or the other. Okay, and also keep in mind that there is an influence between the semiconductor material and the emitted color. Okay, so depending on the semiconductor material that are used for fabricating the LED, we are transmitting information in some wavelengths or the other. Okay, so we can create different colors of lights. So now let's talk about which properties are useful in terms of communications of the LEDs. Okay. So of course the power transmission of the LED is very important. Okay, so the larger the power transmission, basically the larger the SNR at the receiver side. But also it's good to know that, well, here I have included some schematic in which we have an LED who has a photodiode, we have a half power semi-angle, which is the power in which the optical power transmitted in that direction is 3 dBs lower than the normal direction. Okay, so the larger the irradiance angle, the lower the optical transmitted is. Okay, and also in the photodiode we have an incident angle which affects also the communication, and we have a field of view. Okay, so if the incident angle is larger than the field of view, we are not receiving any information. Okay, this is obvious. So this is modeled by the Lambertian law, in which we have here some Lambertian index that can be modeled by this equation here with the half power semi-angle. And this Lambertian emission order can be changed by using some optical devices such as collimators or some others. Okay. So don't forget that VLC is for communicating, but basically it's also for illumination. Okay, we don't have to forget the true side is for VLC. So we have to comply with some regulation in terms of illumination, okay? And basically we have to comply with two metrics, okay? The average illuminance that has to be larger than a certain value, and also the illuminance uniformity, okay? The illuminance uniformity is because the human eye cannot or shouldn't detect differences in the same area, okay? Differences in illuminance. Otherwise, it will be really bad. So in order to calculate the illuminance at one polar coordinate like this one, we have to multiply this variable here, which is the output luminous flux of the LED, which is measured in lumens, okay, and it's computed with this equation here, where we have here the luminous efficacy, which is a characteristic of an LED, of the LED, multiplied by the optical power that is transmitted. Okay, so this is the lumens that is transmitted, and it's multiplied by the free space channel. This sum here is because we have several access points, not only one, divided by the area of the photodiode. Okay. So also it's very important to see, or to know that the LED, the transfer function of an LED is similar than in the high power amplifier of the radio frequency technology. Okay, we don't have a linear response of the transfer function, so we have to be careful and we have to try to work within the dynamic range of the LED. Okay. Otherwise, we will create some distortion in the transmitted signal, which will be really difficult to detect at the receiver side. Okay, so basically we have here a linear range of the LED, and we should try to work within this dynamic range. Okay, here we have the saturation point, and we have to be careful when we work with, for example, with some modulation schemes that has a large peak to average power ratio, which is a ratio between the average of the signal and the highest peak of the signal. For example, the OFDM scheme has a large peak to average power ratio, and we have to reduce this peak to average power ratio in order to make the signal distort as lower as possible. Okay. So in summary, we have to use a scaling factor. This is the input of the signal. The input signal, we have to multiply by the scaling factor in order to scale the signal within this dynamic range, and also we have to add a DC bias in order to make it work in this point over here. Okay. So this is similar. I don't know if you have some experience with high power amplifier, but the process is more or less the same as in high power amplifiers. Okay. So in summary, we can say that the optical power can be measured through the electrical to optical conversion efficiency multiplied by the forward current, okay, to the LED. And also it's good to know that okay, this is well, as I said before, we have to create a white light in order to communicating, and this is the diagram, the CA1931 diagram, chromaticity diagram that contains all the possible colors that can be created, okay, and can be created and can be detected by the human eye. So if we work in this region here, which belongs to some points of the Planckian locus, the Planckian locus is this line over here, okay, and it gives you some CCTs, which is that can go from 2000 kelvins, that is over here. It means that we are transmitting a warm light because it's closer to the red color, and we can work until 6500 kelvins, which is a cooler white. Okay, so we have to transmit information. We have to use the light within this range over here. But it's important to compute or to know by using one LED which kind of color I am transmitting in reality. Okay, so imagine that we have a trichromatic LED like here, and we have the power spectral density of the LED with some energy in the corresponding wavelengths. We have to multiply this spectrum by the color matching function, which are the functions that are emulating, let's say, the bastons that have the human eye, and then we will get these three values, capital letters, and we obtain the axis value of these chromaticity diagrams. Okay, so this is the process in summary about how to obtain the chromaticity in which I am transmitting information, okay? The chromaticity of the light that I am using in my prototype, okay?